All right, guys, welcome back. For today, we will be discussing related rates. Okay. All right. So this will be one of your first opportunities to have the chance to apply your knowledge of derivatives to more of a real world application. Okay. So first, let's discuss kind of like a strategy that we will utilize. Okay. Before we even dive into what they look like. Okay. So the idea here is you're gonna be given problems in which you're gonna be provided a situation in which, as time progresses, things should be changing, and they're all related to each other. Cool. So once we get to the problems, you'll understand a little bit better what I mean by that. But let's come up with a strategy of how to do this. Okay. First, what I would suggest is that you need to identify quantities that are known versus quantities that are unknown. That's going to be a key component for us to solve this. Secondly, and what's really important about this one, and some students have struggles with this, is you need to identify what is changing as time progresses and what is not changing as time progresses. Because what's not changing will make the calculus of this a lot easier. Cool? Let's keep that in mind. Third, then we need to come up with some type of equation that relates all that. And the easiest way to do that, and I forgot to write that, is to probably draw an image for it, right? So draw an image. And based on that image, then maybe you can come up with an equation that relates everything together. Cool? And lastly, once you have that equation, you're gonna take the derivative of that equation with respect to time. Okay, because all of these problems are gonna be about something changing as time progresses. Cool. Step 5, if you want to write that down, will basically be like, okay, once you have the derivative, then you should be able to find the unknowns. Cool. So let's look at a very simple situation to begin with. Okay. So here's my example 1. All right. So we got a hot air balloon that is rising straight up from a level field. Okay. There is a rangefinder that is located 500 meters away from the liftoff point. All right. At the moment that the rangefinder's elevation is showing 45 degrees, that angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay. First, I'm going to come up with a drawing of what this situation looks like. So we have a level field, and we have a hot air balloon. So I'm just going to draw a little box. Here's my hot air balloon. Cool. Now that hot air balloon is going to be moving upwards. It's going to be rising. Okay. We know that there's a rangefinder. So what a rangefinder is basically going to help you measure angles and distances. So we know that there is a rangefinder that is 500 meters away from the liftoff point. So I'm going to call this is my hot air balloon. And I'm going to call this little box over here the rangefinder. Okay. I know that it's 500 meters away. So I'll label that as 500 meters. And that's about it. What I do know is that basically what it does is it's going to help you measure angles and distances for this scenario. Cool. All right. So what do I know about this situation? Well, as the hot air balloon is on the ground and as it begins to go up, and what I knew for sure is that I'm going to call this angle theta. That angle should be changing as time progresses. And what I also know is that like this distance, which I'll just call h for height, should also be changing as time progresses. I can call this like x, but this distance should also change as it progresses. But what I am 100% sure of is that as long as this, and the problem says straight up, as long as that balloon is not moving horizontally, it's just going straight up, then the distance between here and here is 100% 500 meters. Cool. And like I said, one of my very first 2 steps was not only to identify what I know, what I don't know, but also identify what changes and what doesn't change. Okay. So now, back to the problem so I can determine what information I was given. Okay. So I was given 2 things. I was given an angle. I was given an angle that is 45 degrees. All right. I was also given this 500, which I've already utilized, but I've also given this, which I need to interpret. It says 0.14 radians per minute. So that's a rate of change. It's a rate of change that's comparing radians to minutes. Now, both of those are units of, one of them is units of time, and a radian is a unit for angle, which means I was given the rate of change of an angle over time is equal to 0.14 radians per minute. Okay. What do I want to know? How fast is the balloon rising at that moment? Okay, so I'm looking at how fast. So I'm looking for speed. So the speed of the balloon should be represented by the change in the height over change in time. So what that means is I am looking for what is the change in height over change in time. Oh, which in this case, based on the units, I could tell that the fact that this is 500 meters, then I'm going to use meters, and the fact that this is per minute, then I'm going to use per minute. Cool? So now, I've got all this information, I got this drawing, so I have to figure out an expression that would relate theta with h. So I'm like, okay, I have theta, I have h. I did label this as x, but I really don't know anything about x. I was not given anything about x. So I think it's a good idea for me to come up with an expression that I can relate theta and h that doesn't include x. So I'm thinking in this case that I can use the opposite side and the adjacent side. So I'm thinking I could use the expression tangent of theta is equal to h over 500. Okay. So I've identified that. Now it says I'm going to take the derivative of this with respect to time. All right. First, I'm just going to do a little algebra just myself, so I don't have a fraction here. I'm going to move over the 500, so I'm going to have 500 tangent theta is equal to h. And now I am going to take the derivative of this expression with respect to time. All right, so the derivative of tangent of theta is secant square of theta. Now remember, because this variable is theta, and I'm trying to take a derivative with respect to time, I have to think of this as implicitly. So that means that this will be the derivative of 500 tangent theta will be 500 secant square of theta d theta dt. And with the same reasoning on the right side, the derivative of h with respect to time, since h is not t, implicitly we're talking then about dh dt. All right. So I've got an expression here I've derived. And I need to figure out what dh dt is, which wonderfully, it's by itself. So in order to do this, all I need to know is what is 500 secant square of an angle, which the angle that I was given was 45. And then my change in theta over time, and I'll be good to go. So make sure this fits the screen before I start writing. Yes, okay, I'm gonna go over here, I'm gonna say, all right, so dh dt is equal to, all right, I got my 500, not a problem. All right, now I need secant of an angle. Well, that angle was 45 degrees, which is the same thing as pi over 4 if you want to use radians. So back to the unit circle, so pi over 4 on the unit circle. So here's pi over 4, and remember that the coordinates of that location are root 2 over 2, root 2 over 2. And I remember that secant is the same thing as cosine. I'm sorry, not the same thing as cosine, it's the reciprocal of cosine. So the cosine was root 2 over 2, which means the secant is 2 over root 2. So it's going to be 2 over root 2 squared times the change in the angle, which happens to be 0.14. Cool? So now let's just go ahead and multiply things out and see what happens. So dh dt is equal to 500 times 2 squared is 4, square root of 2 squared is 2, and then we have 0.14. All right, dh dt is equal to, that will be 500 times 2, which is 1,000, times 0.4. So really, I just got to multiply this by each other, so that gives me 140.0. I really didn't need to write that zero, sorry, I was just trying to do mental math on my brain here. Because I just multiplied 14 times the 1, and I don't have the 3 zeros, but I have to move it 2 decimal spots. So what does this mean? I gotta interpret. dH dt means the distance, the change in distance and height. Now that height should be being measured in minutes. I'm sorry, not minutes, in meters. And the fact that this point 14 was measured in times of minutes, then we're talking about that the change in height over the change in time for the specific hot air balloon at the moment in which the angle is 45 degrees is exactly 140 meters per minute. And that's the important thing to recognize, okay? Let me go ahead and say, sometimes like the labeling kind of doesn't make sense a little bit, from my opinion, just as a math teacher. I'm not saying that the change in height over change in time always is equal to this. So really, I guess if I wanted to be a little bit more like thorough, I should say that the change in height over change in time at theta is equal to 45 degrees is 140 meters per minute. And quite honestly, that's really what I should be writing here in order to make sure that I'm answering the question, which it was at 45 degrees, what is happening. Cool? So, this gives you the general idea of what relator rates is. I will do one more example here on this video, just to kind of like get our juices flowing, thinking how to come up with images, how to come up with the scenarios of what type of equations do I need to write, how do I derive it. So I want to do one more example in this video, and then I will make a follow-up video, which I will do a series of more challenging problems just to really kind of like get more practice in there. Cool? So give me a minute, I'm going to erase all this, and then I'll be back with one more problem. All right, and I'm back. So here's our example number 2. We have water that is running into a conical tank, so that's going to be important, conical tank, at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet with a base of 5 feet. How fast is the water level rising when the water is 6 feet deep? Okay, well, let's kind of come up with an image of this. So we got a cone that is standing on its point, so that's going to be something like this. Right? And we have water being poured into it, right? So you got water going in. Okay, so I want you to think about the situation. As water comes in, well, it's gonna start, putting in a volume in it. So I want you to think about what is changing as time progresses. So as time progresses, this is gonna start to fill up because it doesn't say anything about having a hole or anything, so it's gonna start to fill up. So what's gonna change? Well, the volume's gonna change. Cool. The height of the water should change. Now, it sounds silly, but like until it's full, then it basically creates like, the water creates like little different cones, right? As you fill it up, like similar cones as you fill it up, which means each of those cones will have a different radius, which could have then a different diameter, which if I just focus on the circle, which is the cross section, which is on the top, you could have different areas, different circumferences. So I just want you to think about what is all changing throughout this problem. Now, does it mean I really need to know all that? Not necessarily. I have to focus on what they're asking me for and what they gave me. So I'm going to do a little bit more labeling because they gave me more information. I am told that the height of the entire cone, so in this case, it's 10 feet. So from here to here. And that the base of it, so the base of it is now, because it's on its point, it should be at the top. And I know that the entire base is 5 feet. Okay, so that's what I'm given, and I'm given a couple pieces of information here. I got this one, and then I also have this one. All right, so first, I'm given a rate of change. So look at the units. It's cubic feet per minute. So that means that you are given the change in volume over time. The change in volume over time in this case is 9 cubic feet per minute. That gives you a hint of what it is that you need for this, which in other words, if I'm given a change in volume over time, then I should probably come up with an equation of volume for a cone, which the equation of the volume of a cone is 1/3 pi r squared times height. Cool? So, when I need to derive this, so I need to take a look at everything that's in here and try to make sense out of this before I start deriving, okay? As water goes in, does the volume change? The answer to that would be yes. As water goes in, does the radius of the water change? And the answer to that is yes, so it should stay as a variable. And lastly, will the height change? Well, yes, it will too. So that means I have 3 variables here. However, I only know information about the change of the volume, and I'm being asked about how is the water rising. So that means I am looking for dH dt. Now, the units for that based on this should be feet per minute because the height gets measured in feet. And then the unit of time that was used here was minutes. Okay. What I'm looking at also is that they're giving me that when the height is, so when h is 6 feet. All right. The problem now is before I even derive, I am realizing that I don't have any information about the radius, which could be a problem. Okay, so let me show you what I mean by that. Okay, let's hypothetically say that you don't catch that and you're like, okay, here's what I have. Let's start just taking the derivative with respect to time. All right, well, let's do it. The derivative of v with respect to time would be change in volume over change in time is equal to, now this 1/3 pi, I'm just gonna kind of pull it out here. That's gonna be pi over 3. And then I gotta take the derivative of r squared times h, which is a product rule. So I just gotta make sure I take my time with that. The derivative of r squared with respect to time would be 2r dr dt times my height plus, I'm gonna leave the r squared alone this time, so r squared times the derivative of h with respect to time, that would be dH dt. All right, so then I'm looking at this, I'm like, all right, dv dt is equal to, just clean up a little bit, I'll distribute the pi thirds. So for the first scenario, I would have 2 pi thirds RH times dr dt. And by distribution of the other one, then I'll have pi thirds r squared dH dt. So now I gotta look back at what am I looking for, which in this case is dH dt. So I'm looking like, all right, this is what I'm looking for. And in order for me to find that, then I would have to know everything else. So I'm looking at this, I can start substituting some information and see where I'm at. So I know dv dt is 9, so I can replace that. I know h is 6, so I'm gonna replace the 6. So 6 times 2/3, so I'll be 4 pi r. I don't know anything about dr dt, so I'm gonna leave it alone. And then over here, I'm kind of stuck with the same situation because I actually don't know what r is. So I'm like, okay, we have a problem. In order for me to isolate dH dt, I need to figure out what dr dt is, and I need to know what r is. So I need to go back to my drawing to see if I can figure that out. Okay? So here's what I know. I am being asked to figure out everything out whenever the height, so I'm going to go to the side and just draw a similar cylinder. Okay? That similar cylinder should have a height of 6 feet compared to the large, okay? Which means I don't know what this is at the moment. So what I do know is that they're similar, so I can do a proportion. Proportionally speaking, I can say 6, which is the height, is to 10. As I'm going to call this question mark, which actually I should call this, I'm going to call it d for diameter, as d is to 5. Cool, so I'm comparing small height to large height, small diameter to large diameter. So all I have to do is cross multiply and simplify. So if I multiply this over, so 5 times 6 is 30, so 30 over 10 is equal to the diameter, which means my diameter is equal to 3. So at the moment when this is happening, the diameter is 3. So all right, I can actually say then that the radius is 3/2, which I can come back here now and substitute this radius with the 3/2. And substitute this radius with a 3/2, and then I can square it. But that still leaves me with another problem. And that problem is the fact that I need a dr dt. Well, I can read the problem again, and I don't see any information about the radius changing. So I think I'm gonna have to come back here and see if I can come up with another equation, another proportion of this. So I can go back and say like, well, radius wise on the large one is 2.5 feet, and then I can call this r. So I can use a proportion again. I can say 6 is to 10. Cool. As r is 2.5. But I mean, is this proportion? Oh, sorry. Is this proportion that I wrote really gonna help me figure out a change in r? I don't think so. Right? Like it just doesn't make sense. I should be using some type of proportion where I can actually utilize like the entire units that I know of. So what I mean by that is I could say instead that radius to height, so I'm going to do a proportion of radius versus height, should be the proportion of the biggest radius that I will obtain out of this would be 2.5, and the biggest height would be 10. Now I want you to think about why I did this. I wanted to come up with a proportion of this regardless of what the height or what the radius was at any time, okay? Not specifically at 6. So I'm going to cross multiply in this case, so I would get 10r is equal to 2.5h. So now I have this new expression. What I can do to this expression, which by the way, I'll go ahead and solve for r. I would say r is equal to 2.5h over 10, which 2.5 out of 10, that would be 1/4. Cool, so that will give me 1/4 of h. And what I can do at this point is I can take the derivative with respect to time at this location, which would give me the derivative of r with respect to time would be dr dt. And on the right side, the derivative of 1/4 h with respect to time would be 1/4 dh dt. Now I have a dr dt, which means that I can come back here and replace it. So let me go ahead and do that. So I'll go ahead and start simplifying. So 9 is equal to, this 4 times 3/2 will be 6 pi. dr dt will get replaced with a 1/4 dh dt. And then on this side, if I start simplifying, so that's 3/2 squared would be 9/4. So 9/4, so that will give me, if I divide by 3, that'll be 3/4, so that'll be 3 pi over 4 dh dt. All right, so now I can do one more thing here. Let's see, so I have 9 is equal to 6 times 1/4, that'll be 6 over 4. And I'm gonna leave it as that so I can combine it with this. So that'll be 6 pi over 4 dh dt's plus 3 pi over 4 dh dt's. So that gives me, let me go over here, that gives me 9 is equal to 6 plus 3 is 9 pi over 4 dh dt's. I'm going to multiply by 4, so 9 times 4 is 36. Divide by 9 pi, that'll be 9 pi is equal to dh dt. So now I'm going to simplify that and be a little bit more specific. Remember, this is the change in height with respect to time exactly when the level is 6, when the height is 6 feet. So I'm going to say the change in height with respect to time, given that my height is 6 feet, is equal to, what would that be? 36 divided by 9, so that'll be 4 over pi. And let's think about it. This is representing the height. The unit of measurement here that I'm using is feet, so it's going to be feet per minute. Okay? All right, now, I'm going to show you a different way to do this problem, but I'm not going to restart it from fresh, from the beginning. What I think I can do, let's just discuss what made this difficult. What made this difficult is that I had to come up with an expression to figure out what dr dt is, right? So I guess, what if I was able to avoid that from the beginning? Now, I'm still gonna have to come up with this expression, so I'll go back to where it is. So remember, I came up with this expression here, this comparison here. But eventually I came up with the fact that r is this, right? So the other option that you could have done is you could have just gone straight to my volume. So I'm gonna kind of do this little like separately. I could say that the volume, since I know the volume is 1/3 pi r squared h, I can still say this is 1/3 pi, but instead of using the radius, because I don't know any information about the radius, I could replace the radius with a 1/4 h. So I can say this is 1/4 h squared times h, which then simplifying that will give me pi over 3 times, if I do 1/4 squared, that gives me 1/16 h squared times h. So then I can say that the volume is equal to, if I multiply this out, pi over, well, 16 times 3, what is that? 18, so 48 h cubed. And now I can simply just take the derivative at this step with respect to time. So that gives me dv dt is equal to 3 pi over 48 h squared dh dt. And look at that. Not only was the derivative easier, but everything I need is actually already given. dv dt we already know was 9, so I can say 9 is equal to 3 pi over 48. We know the height because the height was given to us. That's height squared, which is 6 squared, which is 36. And leaves us with the dh dt, which is what we're looking for, right? So at this point, I can just say, okay, 9 divided by 36, so I can get rid of that, times 48 divided by 3 pi is equal to dh dt. So now it's just starting time to simplify things. So like this 3, 9 divided by 3 can go into a 3. 36 and 48, they're both divisible by 12. So this would give me 36 divided by 12, that would be 3, and that would be a 4. So then this 3 divided by this 3 is gone, so that leaves me with 4 over pi is equal to dh dt, which, look at that, gives us the same thing that we got earlier, but look at how much work I did compared to what I did here, okay? So the point of me showing you this problem is that sometimes, before I end these videos, the information that you have is not enough, but if you utilize your knowledge of algebra and geometry, you can rewrite a very known expression, like in this case of volume, in terms of just one variable, or I'm sorry, two variables in this case, right? Volume and h, to facilitate the calculus. However, not necessarily impossible to solve with the way that it was written from the beginning. Cool? All right. Then that's where I would like to end this video. I appreciate you taking the time to watch this, and I'll see you guys next time. Take care.